view. Okay, share. I'm going to go to full screen. View full screen. There we go. Okay, I hope you guys can see that.
Yep.
Everyone, good. Okay, I think we're good. So, well, we're back here again. Thanks for coming out and listening to this. So this lecture's got, a fair amount of where the bodies are buried in it. So it's got some technical details. It's not quite such a big overview, but I want to just tell you in practice how you actually do this whole construction. Wait a minute. Now I can't seem to advance the thing. There we go. So really what we're going to be talking about today is how you actually solve the BPS equations. So let me remind you first where we were. We're talking about superstrata, and we're looking at 2B supergravity. We've compactified on T4. We're throwing away the T4, and we're looking entirely at the 6-dimensional geometry. And then there's a choice of a base geometry. And then there are two coordinates, u and v, which are usually the null coordinates related to y and the usual time, where the d1 and d5 sit. And y is compactified on some circle of radius ry. The base metric a priori can be hypercalar, but all we know how to do for superstrata at the moment, and this is a big unsolved problem, is flat R4. And then the fibration vector has to satisfy a simplified version of the condition it had to satisfy. It's simply just self-dual on the flat R4, and we'll talk about what we choose for that later. So we've really dumbed this thing down. It's flat R4. Now, the other thing you should remember is that we have the fluxes for this background, the three-form fluxes in 6 dimensions, and they are encoded in terms of some electromagnetic potentials and some magnetic 2 forms. All of these things on the base. Now, the important, new element compared to previous stuff that on microstate geometries and superstrata, microstate geometries, is that everything here is going to ultimately depend on V in these fluxes. And that's essential because we want to have these left-moving momentum waves on the common d1, d5 direction, and that means it's going to depend on position in that direction, or at least the null position going in that direction, y is minus t or something. Okay, so that's what we're trying to do. And then I want to remind you about the BPS equations. And this is going to be very important in practice, that they are linear systems on that base manifold. And the first layer looks like this. It basically relates the fluxes to the potentials, and the potentials back to the fluxes, and the vibration form. The magnetic fluxes have to be self-dual. And then the second layer comes from, you solve this homogeneous first layer, you take that solution, and you make all these source terms on the right-hand side from this, and then you have another linear system for the function f and the function and the parameter omega. Remember, f is this metric coefficient here, and omega is the angular momentum vector. And then last part of this story is, of course, that once you've picked up the electromagnetic potentials, the warp factor in the metric basically is constrained in terms of the electrostatic potentials. That's just a BPS condition that amounts to telling you the mass, ADM mass, is equal to the sum of the charges. And now the goal is to talk about how you actually go about solving this system in flat R4. And we're going to make this very basic baby steps. But first we need to talk a little bit about boundary conditions. So the metric we've got is this beast. And there are two kinds of boundary conditions you want to construct, one of which is when you have a flat R4, we're going to make the thing asymptotically flat. I'll say what I mean more by this, but just think about this as the metric on R4 for the moment, because I'm interested really at the large row behavior. And then when you go to very, very large distance, if you want it to be asymptotically flat, you want to have this metric asymptotically. And basically it means that almost all of this structure here is going to vanish. But the interesting thing that's going to happen is that this function p, the warp factor, should go to 1. And then you get this minus 2 du dv. And then everything else is going to drop away. And p goes to 1, so this stays flat. So you get exactly this thing. So the goal is to make p go to 1 and have everything pretty much drop away. And to make p go to 1, the canonical way to do that is you take z1 and z2 to go to 1 and z4 going to 0. You could imagine doing something different, but this is the choices that are being made here with Z4 are very much motivated by the holographic dual that you want to describe. And in particular, Z4 involves the dielectric B field flux. So it's really Z1 and Z2 that you mess with, but you could try doing something different. I'm going to be making a whole lot of choices about the class of problems and the particular things I'm going to solve today, and those are motivated because there's a holographic dual configuration one has in the back of one's mind. But there are many, many other choices that have not been explored. So that's asymptotically flat. Asymptotically ADS is pretty much sort of similar kind of game, except you want all this structure to fall away, the betas and omegas, but now you want basically P to go like rho to the -2. And that makes a rho, that turns into, that should probably be, that should be root P goes as rho to the -2. Sorry, because Z1 and Z2 are going to go like rho to the -2, which means P goes like rho to the -4. So that typo, that should be rho to the -4 here. So you get rho squared here. Now you get minus rho squared du dv, which is this term here. And then from here, you've got a 1 over rho squared, which multiplies the d rho squared here. So you get d rho squared over rho squared. And then the usual thing that happens in near brane physics, the rho squared in front of the spheres is canceled by the 1 over rho squared and the warp factor. And so you get asymptotically ADS. So I'm going to primarily focus on the asymptotically ADS solutions today, but I will make a comment about what happens when you go asymptotically flat. But really, it's a choice of, at the end of the day, it's pretty much what's the choice you make for the asymptotic behavior of Z1, Z2, and F. So, two choices of boundary conditions. Now, noticeably absent from this is the possibility that you want to make it asymptotically flat in a more interesting way. Notice that this is asymptotically flat where there's an R4. One of the big unsolved problems is how do you make this asymptotically flat where this is R31 and this is a Taub nut space? So another problem. Basically, what we know how to do is R4 in this space and its corresponding ADS3 times S3 or corresponding to the asymptotically flat thing. We don't know how to make this asymptotic to R31. Okay, so we're going to start with the simplest possible thing, the black hole. So this is as lame and as simple as you could imagine. The vibration vector is set to 0. Everything's V independent and all the magnetic fluxes go away. So the first layer is almost completely trivial. The only thing that survives is this stuff, all of which has to be 0, which basically says all the functions have to be harmonic. The second layer is almost equally trivial. Basically, again, all these sources are going to disappear because these are DDVs, these are DDVs, so no magnetic fluxes. So basically, it all disappears again. And once again, you see there's a harmonic condition on F, and there's also a sort of anti-self-dual or harmonic condition on omega, which I'm going to ignore. So basically, the solution is simply the standard harmonic solutions of black hole physics, extremal black holes. And I could choose a harmonic omega as well and make it rotate, but I'm going to make it simple and just say, look, the solution is not rotating. So if you do this in spherical polar coordinates and you want to make it asymptotically flat, you make z's go to 1 at infinity. Here's a harmonic solution. Here's another harmonic solution. Here's another harmonic solution. And the normalizations have been chosen in such a way as to make things nice in that these are then exactly the supergravity black hole charges. Everything else is being basically trivialized. All the magnetic fields are gone, Z4 is gone, beta is gone, omega is gone. So this is the BMPV black hole without any rotation. So basically a straightforward harmonic solution. Now in the metric, as I said, if you look at large rho, then this drops away and the Z's go to 1 and you get this asymptotically flat structure as promised. But if you look at small rho, then these terms, the Q y over rho, dominate, and everything goes as rho to the -2. And so therefore, you get this precisely what I promised before, that basically you get a rho squared dt squared, or rho squared du dv, and this becomes a rho squared dt squared, and then there is since I've got a qp in here, there is some mixing of the dy and dt, and then there's a d rho squared over rho squared. So at small rho, what's actually happening is that you get an ADS, this thing becomes an ADS2, then this circle, the Y circle, stabilizes in size, and then you get an omega-3. If I turn the momentum charge off, then it would then this would have gone away. QP is 0, and I would have simply got a rho squared dy squared, and I've got AdS3 times S3. But in this instance, since I put on some momentum charge, the momentum charge has the interesting effect of changing the AdS3 into an AdS2 times an S1, fixing the size of that circle. So basically sort of standard game, and as I say, standard game, there is also a, there's a radius of the sphere set by the charges of Q1 and Q5, and QP sets the radius of the circle. And then you have an AdS2 near horizon limit for this object. The horizon, remember, in all this sort of story, the horizon is always at rho equals 0. There is an interior to the horizon. You can analytically or geodesically extend inside for rho squared less. It's actually rho squared less than 0. But we're only ever going to be interested in the exterior region because the microstate geometries aren't going to even have horizons. So the only geometry we care about is the rho positive region. Okay, so that's the black hole. Now, if you want to do something a bit more exotic, you have to start looking at sort of so-called two-centered solutions. Oh, sorry, I forgot I was going here first. So here, I was talking about asymptotically flat black holes. If you want to go asymptotically ADS, and you basically go to the previous solution and you drop the ones. So now I've just got Q over rho squared. And if you shove this in to the metric, then it gives you on the money the BTZ metric. Basically, you have a sphere, or BTZ cross S3. The sphere's radius is set by Q1, Q5. And then what happens is you get an AdS2 looking like vector and a minus rho squared dt squared. And depending on whether rho is large or small, this term or this term dominates. At large rho, it's rho squared dy squared. And so the circle's growing with rho. And that's just AdS3. But as rho gets smaller, this term begins to dominate and the circle stabilizes. So this is the sort of standard BTZ story where you have something that's a nice AdS3 times S3 bowl, which then as you get nearer the scale set by QP, when rho squared is of order QP, that circle stabilizes and it really becomes an AdS2 times S2. So this is the sort of black hole-like behavior that we're going to try and make a microstate geometry for. It's going to be something that carries a momentum charge. It carries D1 and D5 charges. And if you don't do anything else with this lot, you just get the BTZ black hole. The superstrata's job in life is to turn this black hole into a microstate geometry. And so this is the sort of reference point that we'll come to. And that'll become important next lecture when I actually go through an example. Okay, now what I thought I was about to say. So we want to get beyond point sources. And in particular, one of the things that sort of this has been around for many, many years. It goes back to the original black ring literature. But there's these coordinates called spheroidal coordinates, which on the face of it, only a mother could love, but they are actually incredibly useful in terms of any kind of ring distribution. So what you do is you take your Cartesian coordinates on R4 and you replace them by these spheroidal coordinates. And they're spheroidal in the fact that the sort of first complex pair of coordinates is given by this r squared plus a squared times sine theta. And the second one is given by a more normal r cos theta e to the I phi 2. So basically, there's a distortion here by a parameter a. And the importance of that distortion is the following. If you look at the locus where r is equal to 0, then this goes away, so that's 0. But this goes to a sine theta e to the I phi. And if you think about that for a minute, that describes a disk, because a basically of radius a, because sine theta goes between basically minus 1 and 1 or 0 and 1, depending on the range. And then this goes through e to the I phi. So basically, the r equals 0 locus in this thing is actually a disk. And this may be familiar to you if you've ever looked at the interior of the Kerr solution and Boyer-Lindquist coordinates, I think it is. You find exactly the same spheroidal coordinates. And to resolve the ring singularity and look at what's going on in the interior of Kerr, you have to go back to some kind of Cartesian-like coordinates. Okay, so most importantly, there's this locus, which is the disk that's at the r equals 0 point. And if you take these coordinates and rewrite the flat metric, you get something that looks pretty unintuitive. There's this function sigma, which you're going to be seeing an awful lot of this function sigma in this lecture. but it's basically this r squared plus a squared cosine squared theta. And it multiplies these first two factors, and then these don't look so bad. Now, if you look at where sigma is equal to 0, you have to have r is 0, and you have to have theta is pi on 2. And if you look at what theta is pi on 2 means, it means that this is a e to the I phi, and so you see it is the edge of the disk. So this is why sigma is important. Sigma is 0 defines the circle at the edge of the disk. And the other reason why it's important is, well, if you calculate the scalar Laplacian for this metric, you find something else extremely important about it. Notice the sigma comes out as an overall factor. Moreover, notice that sigma is the sum of a radial coordinate and something that involves the angular coordinate. So if you try and solve the eigenvalue problem, the wave equation on this coordinate system is separable. Because if you put this equal to lambda times f, you get r squared plus a squared cosine squared theta times f, and you can separate that. So basically, the amazing thing about these spheroidal coordinates that makes them so useful is that it is totally separable. Here's a function of r, a function of theta, functions of angles, and then this sigma, which looks like it's going to destroy you, doesn't. If you turn it to an eigenvalue problem, it basically separates nicely into something a function of r and a function of theta. So, and then you look at what it is, it's just Legendre functions, albeit slightly more complicated Legendre functions. The other thing that's extremely important about this is that 1 over sigma is harmonic. If you hit it with the Laplacian written in this coordinates, it's trivial to see that it's equal to, it's killed by the Laplacian. So therefore this sigma is going to play a major role throughout our discussion. If you want something that is a harmonic function, but also remember where it vanishes is the edge of the disk. And you see this very explicitly. If you write it back in terms of the Cartesian coordinates and write rho 1 and rho 2 in this way, you see that this only becomes singular when this is positive definite. So you've got to have rho 2 is 0 and rho 1 is a, which is the edge of the disk. So the whole point about sigma, why it plays such a central role in this discussion, is it's the harmonic function sourced by a uniform charge distribution around the edge of the disk. So the reason why we can make so much progress with superstrata in R4 is because the underlying equations are ultimately going to can be expressed in terms of a coordinate system where the Laplacians are generically separable. And we can smear things out onto uniform distributions around edges of disks in a very nice way. Doing this outside R4 is, on the face of it, rather more difficult. Taubnut may be a possibility, but once you start losing symmetry, you start losing the power of this calculation technique. But I'll say more about that later. There may be other ways forward if you try and get away from R4. But R4 is doable precisely because of this nice structure. Okay. So if you're going to do any kind of black ring, supertube, whatever else, these are the coordinates you use because they have the nicest possible structure. Okay, so we'll start with the round supertube. First step there is to take the original singular source. I'm going to work asymptotically ADS. I'm not going to mess with the asymptotically flat. So we take the previous thing and replace the 1 over rho squared by 1 over sigma. And so now we've got a charge source that's smeared around the edge of the disk. Similarly with the D5 charge, and we're not going to put any other charges on this. So now we have still a singular solution, but what we do now is we put a Kaluza-Klein monopole along the ring locus. So we have to now make a non-trivial fibration, and we have to solve this self-dual d beta is equal to star d beta equation, and we want the source to lie on the edge of the disk. So it's going to have a 1 over sigma in it. And then you solve this equation, and there's a really simple solution. So the Kaluza-Klein monopole in these coordinates is very, very nice. You can also add angular momentum. You have to solve exactly the thing with the opposite sign, with a minus sign here. So this is self-dual, this is anti-self-dual. And if you can solve it directly by simply exactly the same kind of ansatz, but now you have a sine squared theta plus a cosine squared theta. So self-duality or anti-self-duality just flips the sign here. I've normalized these identically for a reason that will become apparent in a minute, but a priori, these could have 2 different functional coefficients. So what we've done is we've taken the D1, D5, and if you remember the first lecture I said, if you want to desingularize, you want to do the supertube transition, you take the singular D1, D5 2-charged black hole, you put it along a profile, you add a Kutzerklein monopole along the ring locus, and you add angular momentum. The angular momentum has to be tuned in the right way to desingularize it. But this is basically what we do. And then we start looking for the metric smoothness. So we want to shove all of this into this metric. And there's various important things to note. First of all, you want to look at the metric along the locus at sigma equals 0. And the thing you find immediately is, remember, P, since Z1 times Z2 is 1 over sigma squared, root P has a 1 over sigma. So that's bad. And that 1 over sigma multiplies ds4 squared, and in particular multiplies d phi 1 squared, the angle going around here. But also you get a similar term because 1 over sigma here, well, 1 over sigma gives you a factor of sigma, but beta times omega contains a sigma 1 over sigma squared. So you get identical terms basically along the ring from this product and from here. But notice that there's a P and a root P here and an upstairs root P here, which gives you basically a difference between this term and this term with a relative factor of Q1, Q5. And there's a minus sign. So as a result, if you want to cancel the singularity, you have to tune the singularity here to be killed by the singularity here. And you can do that, and that's called the supertube radius relation. So that's the first thing you desingularize. And when we do the examples next time, you'll see a considerable generalization of this supertube radius relation when we do superstrata. So that's the first step, but we're not done. And we're not done because there could be still closed time-like curves. If you remember in your curve solution, there are always closed time-like curves above the ring singularity. However, there's no singularity anymore, but there still could be closed time-like curves. We have no horizon, so we have to get rid of the closed time-like curves. And that turns out that basically you have to require that omega plus beta. If you look at this metric, and you look at the coefficients with d phi dt, which can give rise to a closed time-like curve, they basically come from omega plus beta, and you've got to make that vanish as you get to the ring locus. And that's what fixes the fact that I chose this constant equal to this constant. It kills off those problem terms at the horizon. So basically, basically the relative normalization of these two terms is set by the absence of CTCs, and this Q1 and Q5 are tuned to A by requiring there's no singularity. And when you make those choices, you can rearrange the metric. And you rearrange that metric, and it becomes on the money global ADS3 times S3, with some angular momentum going on here and some mixing between the coordinates along the brane and the coordinates in the sphere. But it's on the money global ADS3 plus S3. And as a result, R is 0 is not singular. It's a bowl. So this is the sort of archetypical starting point of what Samir started with the fuzzball program. He said, look, if you take the D1, D5 system, add a Kutzerklein monopole, and the right amount of angular momentum, and choose the parameters in the right way, you wind up with a beautiful, smooth geometry. And in particular, it starts off that this thing is the holographic dual of the maximally spinning Ramon-Ramon ground state of this D1, D5 CFT. I'm only going to allude briefly to the conformal field theory as we go. But this is the vacuum state that we're going to start with. So what we're going to do is we're going to start with the supertube, which is this sort of stuff, and we're going to add bits to it. So we're going to take this and add more because we want to go to the V-dependent excitations of the system. Okay, so what's the recipe? Remember the whole solving the BPS equation says you pick your geometry and you pick your vibration. So we're going to take flat R4, and here's the vibration, exactly the Kutzerklein monopole moment of the supertube, because I want that system. But now I'm going to allow excitations that are that depend on fluxes that depend on V. And I've written them schematically here. I've dropped the indices because there are 3 sets of equations that basically have this form. And we need to solve them. And we want to solve them, and we've got 3 U1 isometries. Remember, we don't make it U dependent because that breaks the BPSness. If you want BPS, you can have it depend on all the other variables, but the other variables, V, phi 1, and phi 2, are precisely U1 symmetries. And we're going to allow a fully general superstratum to have a completely general phase dependence on V, phi1 and phi2. There's going to be some restrictions in a few minutes, as you'll see, but it comes from all sorts of smoothness, boundedness, supersymmetry, and holography tell us that there's some seemingly rather strange restrictions on these quantum numbers. That will not become clear in due course, but in the holographic story, N and M and K are occupation numbers of various excitations, and so they can't be negative. But you'll see more precisely from the supergravity perspective where this comes from. Okay, so the other thing that's also an important part of first step is we need to start parameterizing these self-dual forms that turn up in these equations. And in particular, there's a very convenient basis, which is in every one of the literature on this subject, which is basically simply some self-dual two forms written on the R4 base in these funny spheroidal coordinates. It's just a very useful basis. And then there's a magical function that turns up everywhere. And you should think of it as sort of like, I tend to think of it as like the generalized version of some YLL. It's basically some power of this ratio, another power of this ratio, and then some mixture of sine and cosine. And I'll make that more precise in a minute. That function is going to turn up all over the place. And in particular, I'm going to present the solutions, and then I'm going to give you an idea of how you make them. So what is called the original class, this is the class we first obtained, or at least I think it was Rodolfo, Stefano, and Masaki who first obtained this. So basically, the first class of superstrata modes, the first set of solutions to this are these. I'm using small letters and the mode numbers to indicate solutions to this equation. This solves this system. And it's written in, here's the phase dependence, here's the phase dependence. You can shift the phases by anything you like, but we've just chosen to write it as cosine and sine. But basically, it's rather unintuitive, but it does involve this function, delta KMN. And then there's a second class of solutions, which was constructed recently by Nate and Stefano. I can't remember, I think it was Stefano Rodolfo. Some permutation, but Nate certainly. And these are called the supercharged class, and I'll explain the origins of these terms. And interestingly enough, the supercharged class has no z's. It's purely in the flux, whereas this has some leg in the z's and some leg in the flux. But the claim is that these solve this system of equations, and they're a beautiful, simple class of them. But the thing that's also you can see immediately from the solution is where these limits come from. That you have to have m as 0 is less than m is less than k, because you see what happens is that if you don't respect these limits, you get inverses of sine or cosine if you don't respect this set of bounds, which means that singular at theta is 0, theta is pi on 2. And similarly, if you don't have n positive, you get some 1 over r's. So basically, the non-singularness of the solution tells you you must take these bounds on these quantities. So a priori, this is not a problem, but the takeaway message is for these solutions, smoothness tells you you've got to put bounds on these phases the way I've written them. And it turns out that those bounds are precisely what you need also for occupation numbers in the dual CFT. So that's kind of cool, smooth. A sort of running theme in this discussion is that smoothness will always tell you something about the CFT. Okay. So the obvious question is, where the hell and how the hell did we get these things? Where did we get them from? And I'm going to probably do violence to this, but I want to give you the rough sense of how it's done. And Nate, please jump in if I'm saying something wrong or stupid, or anybody else for that matter. So basically, there's a generalization of the supertube story I gave you. I did this calculation before with simply a round supertube, but you can make the supertube in R4 have any generic profile you like. And then this is a sort of 1 over rho squared away from the, so this is a charge distribution now smeared along a profile defined by F. Similarly, another charge distribution along a profile defined by F. The metric is flat, F is 0. And then beta and omega are given by the sums and differences of these A and B, which are also given by smearing along the profile. This is the sort of Luhn-Mathur supertube, which basically was shown to be completely smooth and flat space. And if you take it to be the round profile in R2, you get exactly what I said before. Whoops, what's going on here? So the way you'd get these solutions is you start with the round supertube, you make this a round profile, and then you linearize around it. And one of the ways, when you linearize, one of the ways you can linearize is you see that you can make this profile function vary as you go around the supertube. And that can give you a varying relative density of the D1 and D5 charge as you go around the supertube. This has no F in it, this has an F in it. By reparameterization invariance, you can put sort of an F here and a 1 over F here. It doesn't really matter, but the point is that by linearizing the simplest way, where you don't change the shape, you can actually change the density of D1s and D5s in a very particular way. And this produces a linear, if you linearize, it produces what I'll call the seed solution, and it actually has these quantum numbers, K with KK and 0. So simple, obvious thing to do, linearize around the profile. So far, we haven't put any momentum on there. But now you can act on this seed solution with the linearized bosonic symmetries. You've got you've got the rotations on the sphere. So you've got SU2 and you've got SL2R on the ADS3. And you can act with the symmetry generators of that. And that is, in fact, how you get that original solution. Similarly, the new element, which is the more recent paper, the supercharged solutions, obtained not just with acting with the bosonic symmetries, but you can also act with the linearized supersymmetries. So that's why it's called supercharge. So you start with the seed solution, which is obtained from the D1, D5 system. It has 8 supersymmetries. And then you can act on it with these symmetry generators and just rotate them, and it makes another linearized set of solutions. And those solutions are precisely what I exhibited before. So a way you can think about this, and the way I think analogously about it, is that the previous, let me back it up, these solutions are obtained from some deltas that look like this, and then they basically get some phase dependence. So what actually you can think of it as like saying, well, I know what YLL is in spherical harmonics. It's an extremely simple function. It's sine to some power e to the IL phi. And I can generate all the associated Legendre polynomials and all this other YLM crap by acting by J minus. And this is a much more sophisticated version of doing just that. You start with a very simple solution that you can figure out what it is based on linearizing the D1, D5 system. And then you act with every symmetry generator you've got and see what other kinds of things you get. And so you wind up generating all these. This is a huge amount of work, and lots of very smart people did this, but they gave us these solutions. And Masaki and Nate and Rodolfo and Stefano and so on were very central to doing this. Okay, so that's how you get them. Now, the point is that these are solutions to the BPS equations. They're generated by a simple linearized symmetry actions on a simple linearized solution. At second and higher orders, the symmetry action will create all sorts of corrections. So if you want to get these solutions to higher order, you have to work really hard to do second and third order. But you're doing something stupid. This statement, this is irrelevant. You can throw away all the higher order corrections. You have a linearized solution. You've got to remember now that the BPS equations are linear. And if you've got a linear solution to a linear set of equations, you are done. This is the power of the linearity of the BPS system. You don't care about the fact that second, third, fourth order rotations are required to complete the solution. All you need are the linear bits. And so therefore, the linearized solutions are correct to all orders in the BPS equations. You don't have to think any more than that. And so therefore, in addition, you can also take arbitrary superpositions, which are nowhere near symmetry actions. So you started by doing something totally trivial. You started by taking a seed solution and rotating it, and you generate a simple other solution. But it's a symmetry rotation of what you already had, so you've done nothing. But if you did the full symmetry rotation, you'd have to do the whole exponential rotation process, but that would be a nightmare. But you don't need it. All you need are the linear pieces. Moreover, you could then take those linear pieces and superpose the hell out of them. So the fact that the BPS equations are linear is just making this so straightforward and viable. And so now you can take generic Fourier sums of all of these modes in all sorts of combinations. And these things represent shapes on the ADS3, and these are shapes on the sphere. And then with the original and supercharged modes, with the generic Fourier series, you now have two arbitrary functions of 3 variables. at least. So basically, the input here is you've got the linearized solutions, but that's all you need to, in principle, generate the solutions for the entire superstratum at nonlinear order. I've been talking a lot. It's been very quiet. Is everybody with me at this point? Any questions? Any concerns? They've gone very quiet.
I'm happy. Oh.
Any comments? Question? Questions, comments,
Younger
issues?
people should ask. I know this.
Yeah, I'm pausing because I've been going for 25 minutes or so, no, half an hour now. So please, any questions or comments? I'm willing to go back.
Perhaps I would have a slightly physical question, right? Beyond solving these equations. So we have these different functions and forms inside the solutions that we're trying to solve, and inside the equations that we're trying to solve. Can you explain a little bit, perhaps, what are your interpretation of the physical, like, what do they encode? For example, we have like omega, which encodes the angular momentum. But I never really know what, for example, what beta is there for, like the KK modes. What do they encode physically? Okay,
so in my, I can't remember this first or second lecture, I told you what Z's and theta's encoded.
Yeah. So these are the electric modes and the fluxes.
Okay, so beta. Okay, let me just escape out of this for a second and go back. Beta is simply part of the geometry. Where's it gone? Maybe back a little bit further. I'm looking for the three-dimensional metric. Where's it gone? Keynote. Oh, there we go. So basically, beta is this vibration vector. So that's not a good answer. Beta, remember, is if you went down to 5 dimensions, beta is another magnetic field because d beta is what's sometimes called theta 3. So from the 5-dimensional perspective, this is a magnetic field. And from the 5-dimensional perspective, that's another electric field. So you can think of the 6-dimensional metric as saying, well, let's take the 5-dimensional microstate geometries and use these as Kaluza-Klein ways to uplift and get the Y fiber non-trivially fibered over the base. So beta is fiber data, but you can think of it from the 5-dimensional perspective as being just another electromagnetic field. Mm. I don't know whether that answers your question, but also the very important point is that, where's the supertube? Here it is. Oh, the supertube is, from the point of view of the supertube, it's extremely important that this fiber is present and this beta is present because it desingularizes what is a priori an extremely singular solution. So in other words, this is what Samir told us way back when, that basically if you start with a D1, D5 solution, this is a terribly singular smeared black hole around a circle. But if you turn on this Kaluza-Klein monopole and you turn on angular momentum, it makes a completely smooth microstate geometry. And it is going to be the ground state of the system I ultimately want to do. So from the point of view of the microstate geometry, this is playing a critical geometric role to desingularize what is a very bad piece of geometry.
Yeah, I always thought about it as, it's even if you have like formulas for asymptotic values of the angular momentum, it always contributes to that point. So I thought that it's something that smoothens the geometry out. And I see like that is more or less its form. But I thought like, can you a priori, when you have, if I think about a physical profile, can I say, well, this will be turned on without any, smoothness considerations or something?
Okay. I guess there's another consideration which I went through in the very first lecture, which was to say, you can ask the question, if I got a D1, D5 system, is there a way I can give it some shapes and shape modes and still preserve the same set of supersymmetries? So this is sometimes called the supertube transition, but there's another issue embedded in this, which is I want to give this thing not just, I've chosen the trivial case of a circular profile, but I can ask the question, how can I take this system and give it a shape profile in precisely such a way as to preserve the exact same supersymmetries the system had originally? And then you would find you would have to turn on this Kutzkheim monopole and this angular momentum in exactly the way described, with the same normalizations and along the same singular locus. So this process is an answer to many questions. And whether it's singular or non-singular is neither here nor there in that description. There, the goal is to give yourself some shape profile for this, preserving the same supersymmetries of the system you want in. And the added bonus is that in the D1, D5 system, this also produces a smooth geometry. So I guess I'd say if I want to put in a huge new moduli space of shape modes that I can put on here, which is what Samir was doing in the original Luna Mathur story. Where'd it go? Yeah, this sort of thing. This is the addition of an arbitrary, shape profile. But you could anticipate that from the sort of considerations I put in the first lecture, which is I start with some charge Q1 over L, Q5 over L. Can I deform it along a profile in such a way that it preserves exactly the same supersymmetries as I started with? And the answer is yes. And it's done in this way. But you could have anticipated that it needed KKM and it needed angular momentum, basically because of that request to keep the same supersymmetry. Did I do any better, Matt? Yes, do you want to throw anything in or have I covered the bases, you think?
Sorry, there's another way to think about it. Maybe, it's easier if you look at the 6-dimensional metric. Essentially, in the 6-dimensional metric, you have the D1, D5 common direction, which you can call Y. And then you have the R4, but you can write R4 as a Gibbon-Hawking fiber with psi and the V harmonic function.
Yeah.
And then at the center of so R4 basically can be written as a U1 vibration over R3. The U1 vibration collapses at the origin of R3, and that's very nice. And together they form an R4, and then you have the Y direction, which is constant size. What beta does, when you go to the supertube location, it takes the D1, D5 common direction and the R3. It makes an R4 out of them. So beta fibers the D1, D5 common direction, the Y direction. It fibers it over R3 in such a way that near the supertube location, you get a nice clean R4. But the R4 is formed from the original R3 and beta.
I see.
And Y because of the beta pole. And then the Gibbon-Hawking fiber at the supertube location is just going to be nice and big. So in a sense, there's a nice symmetry between beta and the Gibbon-Hawking fiber.
Yeah.
And that's basically, and in the supertube solution, essentially the two guys, if you're just a mathematician, you say I have two U1 vibrations over R3, and they collapse in various ways. But essentially, beta controls the collapse of one of the U1 vibrations, and the V harmonic function controls the collapse of the other U1 vibration.
There's perhaps another way of saying exactly what Joseph just said, which is imagine what's happening with the supertube. Now, the supertube is running along this phi1 circle or running in somewhere in R4, but it's also running along the V fiber. And so there are two sort of directions here. But if you zoom in on the fiber, you zoom in on the supertube, what you find is it's perfectly normal space. And what's happening is that the direction along the supertube is some interesting null direction, but then transverse to that is an R4. And you think, well, how did it become an R4? I had an R3, but it becomes an R4 precisely because the U1 fiber that you have through beta is being fibered in precisely such a way to make a Gibbon-Hawking realization of R4. So the R4 geometry transverse to the supertube direction emerges precisely in the same way that a Gibbons-Hawking with geometry with a single point is actually R4, but it looks like a complicated U1 vibration over R3.
Okay, would that structure be preserved through any profile that will take, like even if I put a random fluctuation?
Exactly, yeah, exactly. So that's, I think that's actually in Lunin Mathur, or it's in Lunin Maldacena. Anyway, there's a very nice calculation where you just zoom in on the supertube and you go, there's no there. There's a long valley, sort of null direction where the tube is going. And then transverse, there's exactly an R4, but it turns up in these Gibbons-Hawking coordinates, where beta and the vibration is playing the critical role of producing that R4. So it turns the thing into pure geometry. as you zoom in on what seems to be a singular locus. And that's exactly analogous to what happens in Gibbon's Hawking geometries, where you seem to have a singular locus where V blows up, but the geometry is beautifully smooth.
Okay.
So that's the magic of the sort of supertube.
Okay, great, thanks.
Any other questions or comments? So the nice thing is we've got all these solutions, but I want to just say, I just want to now sort of talk about a more systematic construction. So I'm going to take a left turn. Everything I've said here is based on using R4, using the symmetry generators of R4, or using the symmetry generators really of ADS3 times S3. But there's a really interesting question, which is completely unsolved, about how you do this more generally if you had a Gibbons Hawking base. And I want to just say a few little words about that. There's a more systematic construction that Sasha Tukov and Robert and I evolved, which has not fully formulated. It's fully formulated, but to implement it is more effort. And I just want to explain what it means. So the most simple thing you can imagine doing is look at a more general hyperkähler Gibbons Hawking basis. But to keep it simple, I'm going to assume it's got all a U1 cross U1 isometry, so it's axisymmetric. And once again, you can work mode by mode, and where phi1 and phi2, when written in terms of the Gibbons Hawking coordinates, are this psi of the Gibbons Hawking fiber and phi of the Gibbons Hawking base, the axisymmetry. So all you do is you redecorate this thing in exactly this manner. Now, if you work mode by mode, and this is something Robert wrote a nice little paper on, you can now say, okay, there's a combination for a single mode, and you pick your favorite mode. There's a particular combination of this V and psi, such that it's, if you like, orthogonal out to this original mode, which means the whole solution is independent of this combination. And so you can compactify this down to a 5-dimensional solution on that fiber. The fiber depends on the choice of mode, but for every mode you can do this. So therefore, for every mode, you're going to be able to find a solution. The reason why you want to go down to 5 dimensions is that the equations become simpler. Basically, the Maxwell fields the magnetic fields become self-dual, and then the Zs are given by solving this differential equation. So the Z and phi theta equations are now decoupled from one another, and the goal is to solve this one. So the 5-dimensional formulation is easier, and you get there by saying for a single mode, I can always go down on some particular combination of V and psi fibers to get to 5 dimensions. So now the problem becomes 5 dimensions, 5-dimensional one, and you want to solve self-dual, well, harmonic forms on the space. And it's a relatively straightforward thing that just follows from what is well known about Calabi-Yau geometries, that you can pick one of the hyperkähler forms as a complex structure, and then those two forms have a prepotential. And you should think of this as just a complicated way of writing, this is D and D bar. So this is a holomorphic, this is the Hodge, think in terms of Dolbeau, this is a D and this is a D bar. And so it's DD bar of a prepotential. And in particular, if you want it to be self-dual, this prepotential has to satisfy the Laplace equation. So the claim is, in fact, the theorem is, if you're in standard space-time, that any standard Riemannian geometry, that any 1-1 form, which this is, can be written as DD bar of essentially a deformation of the Kähler potential, which is phi. And in particular, the self-duality tells you that phi is a solution to the scalar Laplacian. So solving this equation is not so hard on a Gibbons Hawking base because it reduces to solving the scalar Laplacian. Well, that looks kind of nice. But so in other words, this is pretty, solving equations involving with things with legs is usually rather intimidating on a complicated manifold. But in particular, what happens here is it becomes the scalar Laplacian. Okay, but there seems to be a problem. You seem to have reduced it to solving the scalar wave equation on a hyperkähler Gibbons Hawking base, but there appears to be a problem. The field must be appropriately smooth, theta, you've got to have a smooth flux field, it's got to fall off at infinity. Naively, that would suggest the prepotential should be the same. It should be smooth and fall off at infinity. And if you're combine this with the fact that it has to solve the scalar Laplacian, it tells you that if it's a smooth scalar Laplacian that falls off at infinity and it solves the wave equation or the Laplacian equation, it's got to be identically zero. But that's not true. The whole point is the pre-potential is allowed to be singular and even diverge at infinity, so long as those singularities are removed when you create the theta field. And this is a D and a D bar wound up in an interesting way. So what that really means is the singularities can be phi can lie on carefully chosen holomorphic divisors on the given talking base. So in particular, you should be able to, well, if it's Riemannian geometry, this is standard theory, that you basically, the pre-potentials can be singular, but they have to be chosen in a way that they're holomorphic divisors. Why holomorphic? Because that is required in order for this DD bar operation to kill off the singular behavior. So, as I say, in Riemannian geometry, this is standard theory. What Robert and Sasha and I did was to show that actually this seems to work in ambipolar geometries as well, which you need for this theorem to work. So there is a hope to do this. You can reduce it to scalar wave equation, and then these holomorphic divisors, the thing that hasn't been worked out is what's the systematics of the choice of these holomorphic divisors, and can you actually make this work in full generality in ambipolar spaces? So going to a more general given talking basis is not hopeless. What we have done though is, and Robert's particularly developed this for the supercharged case, is that we know exactly what these pre-potentials are for the standard and supercharged modes. And they're pretty simple things. They're just the genre functions with particular dressings that give them holomorphic singularities. Anyway, so I think there's hope to go beyond this. And I think I think the Taubnut case you can probably do using this technique, although that might be more of a sledgehammer to kill a small object. Okay, so the challenge is, as I say, is to develop this for ambipolar given talking geometries. Okay. So getting back to the main thread, the goal now is to solve the second layer. We've solved the first layer. We've got the solutions that we need. So what that means is we know all the source terms on the right-hand sides of these equations, every detail. So I'm going to label these sources S1 and S2, two-form source and a scalar source. Okay, now the other thing to remember is that the first layer equations come in pairs, Z1 theta 2, well, I've written this twice. It should be Z2 theta 1 and Z4 theta 4. And now you can put in principle, arbitrary mode excitations to all these pairs. But the guidance from holography is there's a known class of holographic states. You don't have to do this, but this is what we did. We're going to leave Z2 theta 1 exactly as it was for the supertube. We're not going to touch it. In fact, we're going to leave theta 1 is going to be 0. And Z2 is just going to be the Q5 over sigma. This is because the goal of this calculation was to get the holographic duals of certain supertube states. If you want to get other, certain D1, D5 CFT states, if you want to do other states, you may want to activate these degrees of freedom. But I am just arbitrarily going to say, leave this untouched. Z2 is this, theta 1 is 0. But I am going to allow Z4 and theta 4 to have arbitrary, this is the original oscillations, and this is the original oscillations, this is the supercharged oscillations, and similarly for Z1 and theta 2. And remember, the supercharged modes don't have any electrostatic counterparts, there's all 0. So in principle, that's the guy I'm going to do, and the only bizarre but arbitrary choice I'm making is to set that, but that's guided by a class of holographic states I'm interested in constructing. Okay, so now we're going to make a whole bunch of general observations for describing sort of how you get into the details of solving this. So the first thing to notice in this set of equations is you've got 5 unknowns because you've got a 4-component vector omega and a scalar function f, but you've only got 4 equations. This equation is a scalar equation, and this equation is only really 3 equations because it's a self-dual 2 form. This right-hand side, these are all self-dual 2 forms. This is the self-dual combination, and this is self-dual. And the number of self-dual 2 forms is 3, and therefore there are only 3 components to this equation. So you've got 4 equations, 5 unknowns. But you have to remember, look at this metric. The u coordinate can always be redefined. If you send u goes to u plus f, it basically shifts curly f by a factor of 2 dv of f, and then the omega gets shifted by a rearranged version involving beta of this. So in other words, there's a gauge invariance. This does not change the BPS equation, doesn't change anything. So really there's a gauge invariance, which you should fix. So that's why you've got 4 equations for 5 unknowns. Really it's 5 unknowns, but there's 1 gauge invariance. So the first step you do is you solve Fourier mode by Fourier mode. And if you have non-trivial V-dependent modes, the obvious and nice gauge is to use this to basically kill off f entirely. So that's what we typically do if it's V-dependent. If it's V-independent, things are actually a bit easier, because if it's V-independent, then basically any dot that turns up here, it goes away. And so therefore it decouples, and this equation here becomes something which doesn't involve omega. And these terms have now gone. So basically you can solve for f, and then you feed it back into this equation and solve there. And with that choice, when it's V-independent, there are typically nice gauge choices, like you can choose omega r is 0, or you can choose omega phi is 0, only theta is 0, you choose something. The hard ones to do are the V-dependent modes, so I'm going to focus more on those. So just solve Fourier mode by Fourier mode and make nice gauge choices. The next really important issue about this is to look at the structure of the sources. And the important issue here is that the right-hand sides are all quadratic in the source data. And so what this means is that since you have linear Fourier modes in, say, Z4 and theta 4, the worst you ever get is a product of Fourier modes. So in other words, you can solve this problem 2 modes at a time, when the mode talks to itself, or when the mode talks to one other mode, but you can never have 3 modes talking to each other. You only ever have to do 2 modes at a time. And that solves the most general problem there is. So in particular, you start off, and the way you solve this, or one of the standard ways of solving this, is you simply start off by simply saying, let's consider 2 modes in Z4 and theta 4. I'm showing an index with Km and N with these bounds. So I'm going to just throw these into the mix, and I want to solve the source terms. Well, the sources look like this. Now, basically, you have all possible ways that this term can talk to this Z4 and theta 4 can talk to each other here. And then you've got all the Z4 squares, and you've got the theta 4 with theta 4. So it's all quadratics you have in this stuff. And so therefore, the moding of the source terms involves where the same modes add, or the 2 modes add to each other, or you get difference modes, where the 2 modes take the difference, or the 2 modes to do different modes take a difference. That's all there is. And then you look a little bit more closely, and you remember that we made no mode excitations here, which makes life a little bit simpler. If you make no mode excitations here, remember Z2 multiplies theta 2. Where's it gone? Z2 multiplies theta 2. And Z2 multiplies Z1. So in other words, what this means is that this thing is really going, in terms of excitations, anything that involves Z1, Z2, theta 1, theta 2 is going to be linear in those excitations. So all you have to do is you just look at all the possible mode contributions to sources that are of the modes that match these. So it's just a tedious case of figuring out where all these 2 mode or mode by mode interactions occur. You only have to consider 2 modes at a time, and you look at all the possible ways they can combine to produce something interesting, and remembering these constraints. Okay, so what I'm going to do now, I'll come back to that case in a minute, is I'm going to just talk about how you actually solve it. And it's a bit of a bloody nightmare, but you write a Mathematica code and it just does it for you. Well, not quite. There's a bit of an art form. So I'm going to take the simplest case. It's actually the hardest case when you have V-dependent modes, but you have the nicest gauge choice where you can kill off F. And so then you have to wind up solving this. Now, again, as before, these are 3 equations, and there's 1 more. So you have 4 equations for 4 unknowns. So if you look at these equations, this is d omega plus star d omega, you can see very simply that omega and theta appear undifferentiated in 2 of the equations. They get multiplied by mode numbers. They come from when you get dd phi 1 of omega r, or dd phi 2 of omega r, or dd phi 1 of omega theta, or dd phi 2 of omega theta. They're multiplied by mode numbers, but they are not, but they appear purely algebraically in 2 out of these 4 equations. So you do the obvious thing. You get rid of omega r and omega phi, in terms of derivatives of the other quantities. So you eliminate, use these just to algebraically eliminate in the other two equations. And the end result is you've now got two second order PDEs in omega 1 and omega 2. Straightforward. In Mathematica, it'll fill many pages. It's totally disgusting, but you know, it gets there. The next thing you do, which is the smart thing that we discovered, is you write it in terms of the sums and differences of omega 1 and omega 2. Because this is actually the what I call omega psi. This is the Gibbons-Hawking fiber component, and this is the Gibbons-Hawking base component. And then what you do is you say, let's just try to let's take these two equations that I've got in terms of omega psi and omega phi, and try and get rid of as much of this as I can, starting with the highest derivative terms. You do that, and a miracle happens. What actually happens is that you can cancel out the omega phi out completely. For some reason I don't fully understand, but it happens. I call it the miracle of the Gibbons-Hawking fiber. The end result of doing this elimination is you wind up with a single second order, almost, not quite the Laplacian, it's got slightly different first derivative terms, acting on omega psi is equal to some source. And the other good news is that you may have had pages and pages and pages of Mathematica at this point when doing this, but this source usually collapses to one term or something really simple. So you now have a Poisson equation with a well-controlled Laplacian, and you basically find the solution. You've got to find the particular solution and the homogeneous solution. Then you substitute back. You've got the solution for omega psi, so now you've got to find omega phi. And it is a truly ghastly equation whose structure I do not understand, but you get it. And then you've got to solve that for the particular and homogeneous solutions. And this, then, the last step of this thing is you're always going to be choosing the homogeneous solutions by requiring regularity of the metric, which usually means regularity of all these omegas. You don't want them blowing up somewhere. So the homogeneous solutions uniformly in this game are fixed by regularity. And that means the omegas, the angular momentum vector of regularity. Now, this part of the game is something of an art form. This art form has been improved greatly over the years, but basically finding the particular solutions and homogeneous solutions is an art form. I say more about it in the notes about how you do it, but roughly speaking, there are algorithms for doing this in high school, but if you're smart, you just guess. And then you start making better and better guesses and you get the right answer. But this is not a precise science at this point, but basically we have many families of these solutions, and so we know how to do this. But it's a linear system and it reduces to scalar Laplacians. As I say, I'd love to know the structure of the Laplacian for omega phi. It has the most terrible first order derivative terms with strange denominators I don't understand. But anyway, it turns out you can seem to solve it. So that's the algorithm of solving this thing. So the key thing is to get rid of the radial components immediately and write it in terms of these angular components, and then regroup everything in terms of the sum and differences. And then a miracle happens that gets you through to the end. Okay, so now the empirical data, when you do this, if you look at this, what I call the sum modes, the ones where the modes add up to make higher modes. So K1 combines with itself, or K2 combines with itself, or K1 and K2 combine. We have a simple particular solution in the Habermas paper. There's a very simple, it fits on one line solution to this. But the thing that kills you is that there's no known homogeneous solution that can regularize it. It's got a singular term. It's very compact. It's very simple, but the dr always has a 1 over r in it, or the d theta always has a tan or a cotangent to theta, so it's bad. And so we conclude that if such modes are present, the solution is always singular. We don't know that as a theorem. We just could never find a homogeneous solution. Regular and Stefano and I spent a long time trying to figure out whether we could do it. And the answer is you can't. Well, we couldn't. Doesn't prove the result, but I'm pretty confident there's no smooth solutions to these sum modes. And this gave us no end of grief for about a year, because we thought, oh, this whole thing's going to collapse, until we realized something, which we'll come to in a minute. The difference modes, on the other hand, are, as challenging sometimes, but actually work beautifully. There are many particular solutions, and we've generated infinite families of solutions of these guys. There always seems to be a homogeneous solution that can make it regular, so you can always find a regular solutions for the difference modes. As I say, the solution can actually be a challenge to find, but they never cause regularity problems. There are always infinite families. And the most detailed state of the art, I think, of this is the paper I wrote with Daniel and Robert and Pierre and so on, where we constructed the holomorphic constructions of these things. I'll come to in a minute. So we have huge numbers of families, but the sum modes are a nightmare. Oh, one other thing about the difference modes. Physically, the 0,0 modes, the ones where the modes exactly cancel, K1 is K2, and they cancel out perfectly, are probably the physically most important part of the solution. All these other modes wiggle. They are therefore multipole, higher multipoles. The 0,0 modes are the RMS response. They are the things that don't depend on actually any wiggly solutions. So they contain all the large monopole moments, the momentum charges, the angular momentum charges. So the 0,0 guys are the guys that contain the really interesting physics. The rest of it is just wiggly crap, which can drive you nuts, but it's there. Okay, so these problems, the sum modes are a nightmare. You've got to get rid of them. And basically, this brings us to the subject of what's called coiffeuring constraints. And once again, I'll remind you of the conclusion I made a few minutes ago, that you can solve the general problem, you can solve 2 modes at a time. So I'm just going to start by looking at the coiffeuring constraints for 2 modes at a time. And I'm going to be interested only in the sum modes because the difference modes I know are going to work. So here's the way of this expression is, say, look, we start with the general Z4 theta 4, and I don't care about the difference modes. All I care about is all the ways I can make the sum modes, the things 2K, 2M, 2N, 2K2, and so forth, all the sum of modes from Z1. There are going to be other bits to Z1 and other bits to theta 2, but all I care about are the sum modes for the moment. I say, look, let me look at these sources with these sum modes in, and I put in arbitrary Fourier coefficients in everybody. And you look at what happens, and basically both sources have these kinds of combinations of differences. And you realize that every one of these terms can be made to vanish if you impose these constraints. It seems very artificial. Well, I'm going to say a lot more about it in a minute. But the important point is I've highlighted is that B4, B5, B4, B5, C4, and C5 are freely choosable. They are the parts of Z4 and theta 4. And then B, all these other B's are the Fourier coefficients inside theta 2 and as a result Z1, and they are constrained entirely in terms of those of Z4 and theta 4. So what it's telling you is that the fundamental part of this solution is the Z4 theta 4 guy. And Z1 and theta 2's job in life is at the quadratic order to come in and cancel all the potential singularities and disasters that could be created by Z4 theta 4 sources. So the coiffeuring procedure is telling you that Z1 and theta 2 is fixed entirely in terms of Z4 and theta 4. I'm going to say a lot more about this in a minute, but the point is that it's a procedure that actually works, and I'll say more about justifying it in a minute. But the other thing also, the reason why we got hung up on this, hung up on Superstrata for about a year, was we didn't know that we had to include Z4 and theta 4. And if you, we just had Z1 and Z2, theta 1, theta 2 originally, and we could not get smooth solutions. And it's critical to have this in there. And then Stefano and Rodolfo came along and said, yeah, and in terms of string scattering, you must activate this degree of freedom. Otherwise, you can't get the string scattering is inconsistent. And once again, the holography told us, oh, turn on Z4 theta 4. And suddenly it all works. And that means you can solve these coiffeuring constraints. This one's quite complicated. It's a relatively new insight. So here's the putting it more generally. You get to choose Z4 and theta 4, so arbitrary original solution, and a supercharged solution. And then you've got the Z1 and the theta 2. And the coiffeuring constraints simply say that this guy is entirely determined by when the modes add up to K in all possible ways, and similarly when these modes add up to K. So basically, these Fourier coefficients are totally determined by Z4 and theta 4. So this class of solutions, it's not necessarily the only class, is don't mess with Z2 and theta 1. You get to choose Z4 and theta 4 at will. And this means 2 sets of Fourier coefficients, which means you've got a choice of 2 arbitrary functions of 3 variables. Z1 and theta 2 are then fixed entirely by the Coiffurian constraints. And so the way you should think about this, and I think this contains very important physics, is that Z4 and theta 4 are the sort of leading order or first order seed excitation. And remember its holographic origins. It's in the Nervius-Schwarz B field. It's not in the D1, D5 fluxes. It's in the B field. And remember, we're trying to model stringy modes going up the D1, D5 system. So it's kind of natural to say, okay, the thing you get to choose is the distribution of stringy mode seeds that you're going to have in the D1, D5 system. And then Z1 and theta 2 are constrained RR D1, D5 fluxes. And so the D1, D5 system has to adapt precisely to the stringy modes you've added. And this is the D-brane response. And this is at linear order, and these are all quadratic. So this is first order, and then the D-brane response is a quadratic or second order. So there is a very nice sense in which the Z4 theta 4 is the most fundamental guy, and Z1 theta 2 and Z2 theta 1 are fixed as a consequence of the most fundamental guy. That seems to be what the message of Coiffurian constraints is. There's a bit more. So once you've got those Coiffurian constraints, all that remains is the difference modes. And as I said, I can't prove theorems here, but we have vast numbers of solutions and examples of this. You just start solving the system. There are many, many particular solutions. We've got infinite families. There's always something that makes it regular. They can be sometimes a challenge to find, but we have at least many infinite families. Admittedly, all our infinite families only involve functions of 1 variable. Getting a full infinite family, it's a function of 2 or even 3 variables, is beyond our computational skills at this point, but it's not in principle. Well, the Fourier series tells you can do it. And in the next lecture, I will give an example of one of these things. I want to continue with this Coiffurian constraint business again, just to say a little bit more about it. So the bottom line is these constraints seem a priori a bit weird. They are, however, based on requirements of smoothness. We have particular solutions for these added modes, but they seem to be intrinsically singular. We can't prove that rigorously, but basically smoothness in supergravity tells you have to do this. Now, here's the reason why we know this is right, or one of the reasons we know this is right. These tell you about coefficients of background fields. It tells you about how Z1 theta 2 are related to Z4 theta 4. These are statements, these coefficients can be tested holographically. They can be sensed holographically. They tell you about correlation functions in holographic backgrounds. And this is telling you that one class of correlation functions is related to quadratic order and some other class of correlation functions. And there have been some tests of this by precision holography. I've given the references in the notes, and there are still some more tests. I think David Turton's still working on some examples of this. But the amazing thing is that holography tells us that you have to impose these constraints. So go ahead, yeah. Is there a question? No, okay. So not fully tested, not definitively tested, but a whole bunch of these things. So here we have once again this thing that we've seen quite a few times in this game, that smoothness in supergravity transfers directly into statements that it makes sense in terms of holographic CFT. The holography knows what supergravity wants to be smooth. And so we're very, it's very, well, not very encouraging, it's essential. We are learning precisely about relationships in holographic field theory that are actually testable and true from requirements of smoothness. So this is not some ad hoc procedure. It's actually something that you can test in ADS CFT and it works. Now, I can't resist explaining where we first got this term coiffuring from. Some time ago, Simon Ross and Joseph and I started looking at hair on the surface of black rings, and we discovered that we could make the ride across the horizon of a black ring as smooth as we wanted. What does that mean? It means you can arrange that derivatives of the metric as you cross the horizon can be smoothed out, and you can avoid null singularities and things like that in the hair by adjusting Fourier coefficients in exactly this sort of way for charge distributions on the surface of a black ring. And so we thought it's smoothing the hair on a black ring. We called it coiffuring. That's the origin of the term. But it's exactly this kind of game. I don't know whether there's something, much more fundamental here in the sense of what we're trying to do is make microstate geometries, and microstate geometries tell us that smoothness requires this kind of constraint. Whereas if you have a black ring, if you don't want to hit a null shockwave as you cross the horizon because you've got hair on the surface, you also have to smooth it, and the relationships mathematically are very, very similar. Maybe in some degenerate limit of a microstate geometry, this coiffuring constraints descend into smoothness of hair on the black ring. I don't know. It's an interesting question. Okay, so there's another way to understand this, which comes out of this subject that we've just recently started developing, which is the holomorphy underlying this. But let me pause before I go into, yeah.
Just for this coiffuring, so Simon Ross and us, we used it, to get the black ring to be smooth. But before it, it's actually Samir and David Turton who actually used the coiffuring for something else. They tried to get a neutral black ring.
Oh, interesting! I didn't. Okay.
By flipping the charge, making the charge positive and negative. It didn't work, but
Oh, right, I remember this.
I don't think they're able to do it in supergravity.
Fair enough. Oh, okay. Yes, thanks, Joseph, for the reminder, because there's a little speech I should make here about, because I'm trying to, in this course, I'm trying to throw out things that are unknown. There's a very important idea called the Coleman trick, which is closely related to this, but mathematically at least. And so the Coleman trick is the following, or sometimes called the cue ball trick. So the basic idea is you want to make a gravitational field that's time independent out of time dependent matter. So the interesting question you can ask is, can I make a field be time dependent and yet its energy momentum tensor be time independent? And the simplest way of doing that is you take a scalar field, phi is equal to something times e to the I omega t. So some function of r times e to the I omega t. You calculate its energy momentum tensor, and it only involves the modulus squared of phi, and so therefore basically the energy momentum tensor is independent of t. So there are interesting configurations, one of them called cue balls, where you have an energy density that is created by a scalar field that has a radial profile and an e to the I omega t. It creates some kind of interesting solitonic blob. But this Coleman trick basically involves essentially cancelling out unwanted time dependence from the energy momentum tensor by using a suitably configured complex set of derivatives. Coiffuring is the same kind of deal in the following sense. What did we just do? We managed to kill off all the modes that add. So it's a bit like the scalar. There's no e to the 2I omega t. The only thing that contributes is the difference of modes, which is RMS value. This coiffuring constraint is a much more sophisticated version. But if you go down to a single mode, what this coiffuring trick does is to simply say the modes where they add up are all cancelled out. And the only thing that survives are the difference in the modes. But since you've only got one mode, it's only the RMS value. And so the energy momentum tensor does not depend on the phase. So all this to say that there's this, and that's the trick that I think Samir and David tried, which is to say, can I do an analog of a Coleman trick? Can I make some interesting non-BPS state by making time dependence of some configuration such that the gravity doesn't care? So there's a broader class of really interesting questions in microstate geometries. Can I turn on time dependence in such a way that the energy momentum tensor is insensitive to that time dependence? That would be cool in the sense that you could then maybe make some interesting geometry where there's no gravitational radiation because the metric doesn't know this time dependence. There might still be electromagnetic radiation because that phase dependence might couple to a gauge field, but at least you've managed to dodge the gravitational radiation bullet. So this trick of coiffuring, or more generally the Coleman trick and the trick Samir and so forth used, the trick is just to remember, if you're clever and you pick one mode or do a single mode, you can always arrange that the energy momentum tensor doesn't care. because it involves the modulus squared. It only involves the difference of modes, not the sum of modes. And I think there's a general principle, there might be some exploitation one can do of that in more general non-BPS microstate geometries, because you can make fields depend on time, but the metric doesn't. Anyway, sorry, Joseph, I expand on that theme very, very much more broadly. Did you have any follow-up?
No, that was, I mean.
So anyway, I'm just trying to chuck out ideas that are, I think, ways you can take this. So this coiffeuring thing looks weird, but actually it's not. There's another way to think about it, which involves this thing where we have holomorphic. And this I don't think we've fully exploited. We've started making progress using this formulation, and we've got some really nice, clean results out of it. It's enabled us to develop whole new families of superstrata in new directions. So, as I said, the references will be in the lecture notes. But the trick, first of all, is to realize we got 5 variables, because U is not allowed, nothing's allowed to depend on U. We're going to replace it by 3 complex variables. And 3 complex variables, of course, that's 6 real variables, but there's a constraint. So it's really an S5. And in particular, what happens is that V pairs with R as a holomorphic structure, phi1 pairs with sine theta, and phi2 pairs with cosine theta, roughly. And so this is sort of the S3 part, and this is the space-time part minus the U. So this is really living entirely in the space, 3-dimensional space, and this is sort of in the sphere in the ADS. And then there's some funny normalizations that turn in there. And there's a constraint, and infinity is when R goes to infinity, the magnitude of this guy goes to 1. So basically the north pole of the sphere is infinity. I think we wrote in the paper that was my stupidity, that it's a hemisphere. It's not, I think it's the whole sphere. Anyway, these complex variables are very nice. The reason why is, if you look at Z4 and theta4, you've got this very unintuitive Fourier sum. And similarly, theta does a very uninformative Fourier sum. But if you define the following complex functions, which are just simply take the same Fourier coefficients with these complex variables, and notice how we've chosen the R's over A's and the sines and cosines, that should look suspicious. This is to concoct the delta that turns up in there. And in fact, Z4 is simply the real part, up to a prefactor with this infamous 1 over sigma, of these holomorphic functions. And I've hidden a slightly more disgusting thing, which is the theta4 can also be written in terms of G1 and G2, also maybe 1 or 2 derivatives of G1 and G2, and maybe a primitive where you'd have to take some integrate it to an indefinite integral. But it's a finite expression, it's not too bad. But Z4 is simply the real part of this holomorphic function, much nicer. Similarly, once you do this, you introduce some holomorphic functions for Z2 theta 1, exactly the same deal. And once again, Z1, which is this ghastly thing, simply becomes the real part of this holomorphic function. And theta 2 becomes a bit more disgusting, but it's still the same thing. Oh, okay, I should have said, I should have said that should be theta 2, but okay. I think I've got my Z1s and theta 2s the wrong way around, but never mind. Okay, so basically you introduce holomorphic functions that encode these Fourier coefficients, but then at least the Z's are real parts of these holomorphic functions, and the thetas aren't too bad either. They involve integrals or partial derivatives of these holomorphic functions. Then coiffeuring has a very simple expression. Coiffeuring simply says that H1 is G1 squared, and H2 is roughly G2, 2G2, G1, but in fact, there's some rather disgusting extra thing you have to do to G1, and it's to implement this constraint that basically C1 prime has to be this. Now, why is it a bit more disgusting? Every K you see in the denominator has to be done by doing an indefinite integral of one of these functions, and everything you see in the numerator has to be done by differentiating. So basically you can make this, and this is the 2 G1, G2 is this term, and then this is a set of indefinite integrals or derivatives that implements this term. So, but here's the magic. H is just G1 squared. The coiffeuring constraints tell you that these things are locked to the squares of the things you first thought of. Now, what does this mean? It produces huge simplifications in metric quantities, because what happens is that you wind up with quantities that only involve the modulus squared of holomorphic quantity, or it involves one holomorphic quantity times the complex conjugate of the other. In other words, the metric wants desperately to be not 2, 0, not 0, 2 in holomorphic language, but 1, 1. It has one holomorphic leg and one anti-holomorphic leg. And here's the simplest example. On the face of it, this guy with the oscillation with Z1 and Z2 and Z4 squared could have involved G1 squared, G2 squared, or G1 G bar, G1 bar. And what actually happens is the Coiffurian constraint simply means that this warp factor in the metric, the G1 squareds cancel, the G1 bar squareds cancel, that's Coiffurian, and the metric only depends on the modulus squared of G1. So holomorphy is a very, very natural way of encoding these Coiffurian constraints. It says that things want to depend not on the squares of holomorphic functions or their anti-holomorphic counterparts, but only on the modulus squared or holomorphic thing times an anti-holomorphic thing. This also makes, remember I said the equations of solving the BPS equations, the second layer can be hard, it can involve guesswork. This takes an awful lot of the guess out of the guesswork because you can simply recognize things much more directly. So it makes the simplification of the second layer of the equation. Now it's not uniformly simple. It's not completely simplifies everything because this thing is kind of disgusting and we have no sort of direct knowledge of where this, what the role of this thing is. But it does make a huge overall simplification to the construction of superstrata. There is an underlying holomorphic structure, and the reason why there's an underlying holomorphic structure you should have suspected from the D1, D5 CFT. Remember, these geometries are encoding coherent states, and coherent states naturally have a Bargmann representation in terms of holomorphic variables. Those power series are very closely related to the power series of these G's, and so there's a holomorphy to the coherent states you're describing, and that holomorphy transfers directly over into the supergravity. What the role of the Coiffurian is in the CFT is something mysterious to me, and probably to the CFT people, but it's a thing, and we can see it. Okay. So the last gasp of this lecture before is to simply say, I focused entirely on asymptotically ADS solutions. I just want to say what happens when you go to the asymptotically flat story. So it's the same deal. You put in some Z4s and so forth, and theta4s and Z1s and theta2s. The only difference is there's a 1 in Z. And remember, 1 is a homogeneous solution to all these equations. You can add any damn constant you like. And so there's an interesting game to be played about adding other homogeneous solutions. You can put black holes in here if you really want to. But all you're doing to go to asymptotically flat is you're putting a 1 into Z1 and Z2. That's all. It's the only thing you have to do. So what it does is, of course, it puts a 1 in here and a 1 in here. And so for the ones here will, no, they won't also necessarily die out, but it just puts in, but the bottom line is that it produces new sources in the second layer of equations. And so you just have to find the solutions for those new sources. And those sources tend to be simpler than the ones you've already found. They're 1 times theta1, and that's trivially solvable because you find the prepotential for theta1. So sometimes it's trivially solvable, sometimes you have to work a bit harder, but at the end of the day, you just have to put in some new sources to find the omega's responses and the F's responses to these ones. The funny thing is it does modify the Coiffurian constraints in non-trivial ways because the corresponding Fourier coefficients come in here, and it doesn't tell you directly that that these Fourier modes are related to the squares of these Fourier modes. There are some linear terms that, sorry, where is it? Theta2's Fourier modes are related to the squares of these Fourier modes. There are some linear modes. The linear modes come from the fact there's a 1 times this. Well, there's some the ones come in and give you linear corrections. So it gives you modified Coiffurian constraints. And it does, in fact, mess up the holomorphy in the second layer. There are terms that are still, the holomorphy of most of it survives, but these ones come in and screw up the holomorphy. It screws up the Coiffurian constraints. So holomorphy is a thing that only seems to be part of the ADS3 description. The Coiffurian constraints also get messed up. And so if you remember I said there was this Coleman trick where you can make the energy momentum tensor independent of a mode excitation if there's only one mode. That's an ADS3 thing. If you put in one mode into this procedure, and I'll show an example next time, you can make the ADS3 geometry completely independent of that mode oscillation because the energy momentum tensor is independent of it. But the minute you put a 1 in there, it really does mess up that statement. And in fact, you cannot, the Coleman trick doesn't work when you're connected to asymptotically flat space. So I suspect that has something to do with the following statement. So if you put a mode oscillation to any of these fields, they would obviously want to produce gravitational radiation. They want to try and produce electromagnetic radiation, perhaps. But what happens is that in the ADS3 geometry, it's a box. And so the solution is really that radiation in equilibrium with the system. And so you've boxed it up and you can make something that's actually independent of that mode. But the minute you put flat space on as a boundary, stuff can leak out and the mode dependence comes back. And so there's some really interesting physics associated with how this changes. And I think for the non-BPS case, it's going to be critical because that's how energy will leak out of the system in Hawking radiation. So I made an example. I said there might be some really cool BPS things or non-BPS things you can do with time dependence where the energy momentum tensor is time independent. That I think will only work if you are in ADS in this context. But anyway, this is the word of warning here, that it's very harmless. It makes a modest increase in the degree of difficulty in the BPS story, but in the non-BPS story, I think it's going to contain some really cool physics. But I don't know what else to say there. So I'm basically done. The next lecture is really just going to be, I've been talking in abstract about these equations. I'm just going to tell you a solution, and perhaps the simplest solution there is. Moreover, it's perhaps the most useful solution there is because it's extremely easy to characterize now. And it's called the 10N superstratum. And I'm going to actually think about it in general. So the N, so this is K is 1, M is 0, and N is this N. And I'm going to talk about the most general solution where this is allowed to be a fully general Fourier series. So you can put in a whole function's worth of this stuff. It's not, there are many solutions we have, but this is the easiest one to describe. And if you're interested in just using a superstratum to mess around with the geometry, this is the easiest, simplest one you can describe because it turns out the whole thing just lives in the 3 dimensions. You can actually, the sphere becomes auxiliary. So I'm going to describe the solution in some detail next time, and that will be my last lecture. So I think I will stop here and see if there are any further questions. Stop here, stop share. Questions, comments, issues, concerns? There are 16 of you left. My goodness, that's pretty good.
I guess I'll ask. I don't, is it ever an advantage to work in like another duality frame? I mean, I know in the D1, D5 you have the CFT description, but I don't know. Is there ever any advantage to going?
Joseph's probably the best person to field this question. Let me just say the conservative thing. These things tend to be singular in other duality frames. So remember what I said about the magical thing that really has given us a huge amount of guidance in the superstratum program is smoothness translates into some precise statement about the CFT. So if you don't have smoothness, if you're in some other duality frame, you don't have the CFT, you've lost those amazing guideposts.
Oh,
but that said, it doesn't mean you shouldn't think in other duality frames. So let me give you an example where this is an extremely useful way to think. I've gone to 6 dimensions and I've frozen all the T4 degrees of freedom. I haven't done any back reaction of that, but in principle, you'd like to do that. But in terms of the D1, D5 CFT, adding excitations on the T4 is something like, it should be morally equivalent to looking at excitations just on the S1 that you've already got. So the way one tends to think of this is, okay, the T4 excitations are just going to increase the central charge of the underlying CFT, but they aren't going to do a huge amount more for you. Perhaps not, but another way of thinking, you know, the mileage we've gained is out of this D1, D5 density mode. That's really what's given us mileage. But if you go to the F1P system, that's 1 of 8 transverse polarizations. And so from the F1P system, it's kind of obvious that the mode that we're making a lot of mileage of, the thing that's indexed by K, the KK0 mode, is a density mode in the D1, D5 system, but in the F1P system, it's just one of 8 transverse polarizations. So there are beautiful physical arguments to say, look, how do you extend this to the full system? You go, well, in the F1P system, this mode that we're looking at is on the same footing as every other transverse mode. And I bet you all it does is it increases the central charge. So in a sense, if I prove something in 6 dimensions, I'm getting it for a CFT of reduced central charge. So there's immense value in thinking in other duality frames. But if you want to frame it in terms of holographic duality, there may be some limitations. So, Joseph, you probably usually joke.
Yeah. So first of all, there are some other frames which are better. First of all, D1, D5, you can T-dolarize on the torus. You can make it into like anything which has any T-dollar on the torus. So a D3, D3, where one D3 has 2 legs and the other D3 has 2 legs. That's equivalent. It's the same 6-dimensional supergravity. So that's so the D1, D5 is friends with basically everything else which comes from T-dollarity on the torus. But then if you go away from D1, D5, first of all, I mean, there's a frame which is very nice, which comes from S-duality, which actually Stefano Masai and Emil Martinek and David Turton explored, which is the F1 and S5. So if you S-dualize D1, D5, and especially if you look at 2-charge supertubes, what's happening is that you only have NS fields. You don't have Ramon fields. And when you have only NS fields, you can actually write a full-bloody string theory on it. And you write a string model and you solve the string theory exactly, and you can do actually you can use the full machinery of string theory. You cannot use it on the superstrata, unfortunately, because the superstrata have the Z4 mode. The Z4 mode, when you S-dualize, becomes a Ramon field. So when you have solutions which only have so when you have bubbling solutions, or you have like 2-charge supertubes, when you go to the F1 and S5 frame, you basically have a purely NS background, and then you can actually do string theory on it. You can actually write the string theory, and Stefano and David Turton and Emil Martinek, they really did a lot of very nice stuff in that direction. And in particular, you can actually find some solutions, which is there's some horrible solution which is called JMART, which was found by Simon Ross and Vishnu Jejala and collaborators. And basically using these methods, David and Emil and Stefano, they actually found the JMART solution in this NS duality frame. So that frame is useful, but you need to know a lot of string theory to work in it, which I don't. So I never worked in there, but there are cool people who like working there and so on.
So let me expand. Can I expand on that point a second? I mean, from our perspective, if you go to the NS5 F1 frame, the D1s and D5s have become NS5 and F1, and then the momentum states, which I said are the sort of fundamental linearized modes of Z4 and theta 4. In their framework, you should think of them as perturbations because they can't do the full back-reactive geometry of those modes. But in that framework, you can still think of the NS5 F1, and one of the really cool things they can do is they can look at phases where these branes start getting very close to each other and almost touching, and you can see the emergence of new sectors of the theory. So it's an immensely powerful frame for asking a whole different collection of questions about the sort of phase space of the larger conformal field theory and its Ramon ground states. And as I say, we're very safe. We're keeping a big, fat, round supertube. But the question is, if you manage to pinch off this thing and the supertube starts to touch, or gets close to touching, there are new phases of string theory that emerge. So other frames are incredibly powerful for other classes of questions. Let me give you another example of something which I think might be a very interesting use of this S-dual picture. Emil and I did this probe where we dropped an F1 string into D1, D5 P geometry. If I was going to, an obvious thing is to drop a D1 probe in. If you're smart, you won't drop a D1 probe in. You'll just S-dualize and you'll do the NS5 F1 geometry and drop in a fundamental string into it. Right. So there are many ways in which you can use the other duality frames. And as I say, Stefano Masai and David and Emil have made huge progress in understanding the sort of broader phase-space structure of these CFTs using this other frame.
Thanks.
Oh, another one, of course. This whole game started when Joseph and I started doing M2 as a 3-charge system in M3. So it's extremely useful. But the new element here, Superstrata, there's a set of lectures I gave last year, which is about the old way of doing it. And there's a set of lectures I'm giving this year, which are about Superstrata. They've gone in two different directions. You start with the same two-charge system, and then you can add a third charge by adding some more M2s in one frame, or here we add more momentum charges. You can obviously do both. And this is why I keep alluding to the fact of you could take a more general bubble geometry with more general fluxes, and now you can put momentum charges on that. We don't know how to put momentum charges on three-centered solutions. We don't know how to do it. I've tried to allude about first steps to it, but it's a big open problem. Take the old way of doing things and put momentum modes on it. It's a huge open problem. And Robert and Sasha and I tried to make some first steps in that direction with this this trick of using the holomorphic structure that I alluded to in the middle of this talk. So, the first step, as I was talking to Nate about, is can you do Superstrata on Taub nut? That's already an interesting question, because it's just a little bit less symmetric than R4, but it's maybe too much. It could be very challenging, but it'd be really nice. And that solves a problem where I said at the beginning, we can do asymptotically ADS3 times S3 or asymptotically R4 1 times S1. We don't know how to do asymptotically R3 1 times S1 times S1. That requires Taub nut. So, these lectures are a sort of discussion of what we can do. Joseph, did you have more to add about other duality frames?
No, essentially, okay, there's a way to think of, somehow the miracle was that, okay, at the beginning we worked in this in this 5-dimensional duality frame, M2, 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 and, everything was very happy there and so on. And then when we discovered that, there should be superstrata, what you're expecting is that, so if you look at superstrata and you look at the bubbling of this, so you have a supertube, which is codimension 3, it's a point in R3, it's codimension 3, sorry, it's a point in R3, the supertube. If you look, so again, you're in R4, you have a line, the supertube line. You do a slice, you basically have a line in R3, all the harmonic functions near the supertube go like 1 over R. So what we thought was that in general, if you want to look at a black hole microstate in a random duality frame, you basically have the supertube and you have to bubble it once more. You have to basically do this process called double bubbling. Now this process changes the codimension from a point in R3 to a point in R2. Now points in R3 have a 1 over R harmonic function. Points in R2 have a log harmonic function. And I've never seen a smooth solution in my life with the log harmonic function. They're always crazy. And basically what we believed once we realized that you have to have supertubes with momentum and you have to have the superstrata, what we believed was that these states are going to be non-geometric, they're going to be singular, they'll have logs, there'll be stuff blowing up, they'll not be described by supergravity. Masaki Shigemori spent a lot of time doing this generalized geometry and discussing these objects. These objects are like the 7 brains. The 7 brains, they're basically just horrible, log singularities and so on. And basically we are expecting that, the more generic singularities, the more generic microstate geometries are going to be like that. And then by some dumb luck, which I'm still shocked how well it worked, in the D1, D5P frame, it so happened that because the supertube is pinching the R4 near itself, as I told you before, the Y direction is pinching and so on, this bloody superstrata ended up being smooth. But if I were to bet 2 years before that, I would have said, no way, they're not going to be smooth. I remember arguing with Nick on the phone saying, those are never going to be smooth. They'll be non-geometric and, the codimension is, there'll be codimension, a source in R2. A source in R2 source is a log, a log is never smooth. I've never seen a smooth solution of the log. So somehow in this D1, D5P system, we have been incredibly lucky to get the states to be smooth. Again.
Wow.
There was a long time in my life when I believed that, they'll never be smooth in any duality frame. Maybe there'll be a very, very tiny sliver of states which are going to be smooth. All the other ones are going to be crazy, singular, non-geometric, all the stuff you want. But somehow, wow, until now, we've been really luck has been on our side.
So there's another point I want to raise, which it's like my Carthago delendum essay kind of statement, if you know the history of that. But it's
Carthago delendum essay. You know this?
Carthage must be destroyed. Okay.
This is a Roman in the Roman Republic. those I forgot who it was, Chippy or somebody who kept saying every day.
It was Cicero, or it was Kate. Anyway, the point is that no matter what, he would give a speech about toilets or public works, but he'd always end his speeches with Carthago delendum esse, which means it was the overwhelming political imperative from his perspective. But it is an imperative. This is an imperative from my perspective, and it's related to the following thing. We have two-center solutions. Everything I discussed today was morally a two-center solution. It's essentially because I have these spherical, spheroidal coordinates. There's a center which is the center of the coordinate system, and then there's a center which is the locus of the ring. But it's morally speaking a Gibbons-Hawking two-centered solution. Everything here is two-centered. What's the holographic dual of a three-centered solution? That we have no idea, and there's a really important conceptual issue there. So the point is that in the CFT, the Y circle and the Gibbons-Hawking psi circle are fundamentally different objects. The Y circle is the world volume of the CFT, and the psi circle, the Gibbons-Hawking, is some space in which polarizations, can live. So in other words, it's the internal symmetry space, the psi direction. It's not the world volume of the CFT. But now you can say, okay, let's take a three-center solution, and suppose that two centers are very, very close. I can zoom in on it, and I say, okay, it's a two-center solution. There is a CFT interpretation of that two-center piece. Now I can imagine looking at two other centers and say, okay, what's the world volume interpretation in terms of CFT of those other two centers? And it turns out that the world volume of each of those two different CFTs, depending on how you choose the pair of points, is different. They're different mixes of the V and psi circle, or Y and psi circle. So what's actually happening there is that if you go to one pair of two centers, you say, this is my Y circle, this is my psi circle, good. But then I go to the other two centers, the psi's and Y circles get mixed up. And part of it is a spectral flow, and the other part of it is what we call a gauge transformation. But that gauge transformation changes the configuration space of the CFT for the world volume. Which is completely weird. So there's a deep conceptual issue, which the geometry doesn't care whether it's a psi circle or the Y circle. It's just totally, it's a W1 fibration over R3. So Y and psi are on exactly the same footing. But in the CFT, one is the world volume of the CFT, and the other is a configuration space. Now, the only thing I've ever heard that comes remotely close to addressing this issue, and this is a really random outlier statement, is that JT bar, or JT bar
and JT bar.
Yeah, those two perturbations, there's this integrable perturbation of CFT. And the question, and there's a modulus you can put in front of that perturbation, you can drive it to some new theory. And if you do a little formal calculation, I think Monica told me this, because you do a little formal calculation, it does look like you're doing exactly that. You're trading off configuration space for world volume. I don't know whether any substance can ever be put on it, but...
So going from one, I guess, two-centered solution to another is like flowing along this...
Yep. So let me put it slightly differently. If you've got a three-centered solution, you can stand off at infinity, and you have the same universal D1, D5 CFT with central charge 6M1M5. Now, if you zoom in on two centers, you've got much less flux and much less charge in those two centers. Therefore, it's a smaller CFT with a much smaller central charge, and there's a renormalization group flow that drives you to that.
Yes.
But then there's a renormalization group flow that could drive you in principle to the other 2 points. Now, you can't separate off these two CFTs in the way that I'm saying in geometry you can, because they're going to mix with each other. But in some sense, I would say no. What's going on is that there's a much, much bigger CFT, and then there's a renormalization group flow, and one of those CFTs in the middle is an honest CFT, and then the other one is perhaps some TT bar flow or JT bar flow of the other CFT. To be honest, this is such an ill-formed idea. I don't know whether it works, but the conceptual problem of going to three centers embeds this issue that in geometry, the Y or the V circle and the psi circle are on exactly the same footing, but in the CFT, they are totally different. In the CFT, the V circle is the world volume of the CFT, and the psi circle is the configuration space where the polarization tends to sit. And yet the geometry says, no, they're equivalent. I can change one for the other without paying a single blinking an eye. I can flip them around. They're the same geometry. And this is, from the CFT point of view, there has to be something interesting in this. But I have no idea what it is.
Yeah.
So that's my Cathago delendum essay statement. It's there has to be a...
Yeah, I don't have anything to say.
No, if you did, I would be stunned because it's But any other questions or any other issues, or should we just?
Yeah. Hi. So I guess I have something that bugged me since halfway through the lecture, I guess. So you kept saying that smoothness conditions like inform you something about the CFT somehow.
Yeah.
But surely there exist states in the CFT which should not be describable by smooth solutions.
Absolutely.
So in a way.
Why? I don't know. That's the question.
Okay. Hold on a second. Joseph and I disagree on this. So I'm going to take 2 minutes and give you an answer, and then Joseph can have 2 minutes and give you an answer, and they will be somewhat different. But finish the question first.
Right. So, I mean, that's the question. So basically, these states in CFT that I guess, for example, that do not have these constraints on the N and K and so on. What are, like?
Okay. So let me try and refine. I think I heard what your question is, which is that generally a string theory state doesn't correspond to a geometry.
Yes.
Okay. The question, reasonable people can differ on whether that's true, but let me accept, I believe that's true. I think there are intrinsically string theory states that cannot be described by geometries. But what the statement I'm making in this story is that I'm going to say, let us suppose we have a highly coherent state inside inside the CFT such that it is actually describable by geometry. Okay, so let's suppose I'm in that regime. And now I can ask the question, what are the correlation functions that I can compute in that geometry using the standard procedures of ADS CFT? I can look at 3-point functions and so on, or 4-point functions. And I can compute those 4-point functions. And then what I can do is I say, but there are some 4-point functions that in that geometry are related to other 4-point functions. And when I look at those relationships, I can test the equalities between various Coiffurian constraints on Fourier coefficients in my geometry. So, so long as I work in the regime where I have a big fat geometry, where there's a Coiffurian constraint and there's a big macroscopic thing, I can say, okay, it's dual to a set of coherent states in which I can calculate correlation functions. And so these precision holography tests are all done in that regime where the supergravity is a good description of the coherent state. So I'm not trying to claim one way or the other that smoothness is always going to be a manifestation of a stringy geometry. I don't think so. I think the stringy geometries will be rather choppy. But what I'm telling you is that the bizarre thing is that in supergravity, where you have a good coherent straight description, you find these mysterious relationships required by the fact that there are no singularities in the geometry. And the absence of those singularities translates into a prediction about correlation functions in the CFT. And those predictions turn out to be correct, which is, to me, just magic.
And they're in a way, they're in a way predictions about correlation functions like that, for example, would map coherent states to coherent states or something like that. Like
it's okay. I'm not an expert in this, and maybe there are people here like Nate who could answer this much better. But what my understanding of it is that you sort of start calculating 2-point function, two light, heavy correlation functions. And you find that the Fourier coefficients can be measured by those correlation functions. And typically what you do is you look at the factorization of some 4-point function in 2 different ways and you compare the results. Somehow out of this, you can read off the Fourier coefficients in these backgrounds. There's some papers by David Turton, which I think are where he's done the most recent holographic test, and I did reference them in the notes. I'm getting way out of my depth here. Joseph, do you want to say something?
Yes. So first of all, there's a question. So you have a Hilbert space. The Hilbert space has vectors which are spanning it. The question is not whether a random guy in the Hilbert space is going to be smooth, because we know very well that even for the two-charge system, the Hilbert space is spanned by some solutions, which are smooth solutions. But from a CFT, you can look at the quantum superposition. You can look at like, alpha 1 psi 1 plus alpha 2 psi 2. That's a very good state in the CFT. That's going to be a quantum superposition of two geometries. And that's going to be not a solution of supergravity or anything. It will just be some quantum superposition of two solutions, which is not going to be describable in supergravity as a smooth solution. So the key question is, are the typical states of the black hole, is the Hilbert space of the black hole spanned by smooth solutions, by coherent states? Now, in the two-charge system, it so happens that if you can construct all the two-charge states, or the two-charge solutions, and you can ask whether the Hilbert space is spanned by the solutions, and the answer is it's spanned by such solutions, but the solutions in some corner, they become actually too choppy, and their smoothness is lost. So the two-charge Hilbert space is not spanned by smooth supergravity solutions, but it's spanned by solutions which make perfect sense in string theory. You give them to Stefano Massari, to Emil Martinec and David Turton, they're going to quantize string theory on them, and they make perfect sense in string theory, but they're not smooth in supergravity. The question is, in the three-charge system, what will be the story? Option number one, maybe in the three-charge system, all the basis vectors of this Hilbert space, which are smooth, which are coherent states, which are describable in supergravity as something, are going to be smooth. Option number two, maybe they'll be like in the two-charge case, some will be smooth, some will be choppy, and again, the most typical one will be at the boundary. Or maybe they are worse than in the two-charge case. Maybe most of them are going to be choppy and stringy and, with curvatures beyond the Planck scale. And the smooth guys are going to be a very, very tiny subset. Now, our experience has been that whenever you have a two-charge state, which is singular and choppy, once you put momentum, the momentum actually makes it nice and smooth. And the reason is that the singularity and choppiness comes from the Y fiber. The Y fiber, you can have, let's say you put some fluctuation on the Y fiber, things fluctuate. Once you put momentum, you blow up the Y fiber. So whatever small choppy fluctuation you had, let's say you had like, sine of 15Y, if Y had periodicity, 1 millimeter, sine of 15Y would be very choppy. But, if you make this into 1 kilometer, this becomes a nice, beautiful wave. So our experience, and, we had a paper with David and with them in Martinec and Nick, in which we actually found some crazy singular two-charge solutions. Once you put momentum, the momentum actually makes it nice and big and happy. So this has been our experience, that momentum tends to smoothen out things. So that's why I'm actually more optimistic that in the three-charge case, because you have three charges, the third charge makes the solution happy. You can see this also in the M2 M2 frame. In the M2 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 frame, when you have two charges, things are always going to be small. Once you have three charges, the three charges make the throat of the solution to be as big as the black hole. And then at the bottom, you have some bubbles and you have something. But the throat of the black hole is like, 10 kilometers large. And then you have like, 2 bubbles, 3 bubbles, 4 bubbles. Okay, they'll have half a kilometer, but, they're still going to be large. It's not at all. So as far as I'm concerned, it's not clear at all whether the typical states are going to be choppy or, at the border or smooth. But so far, I've seen that momentum tends to make things smooth. So I'm on the optimistic side. I think.
Let me add to that just slightly. I mean, so I completely agree with everything Joseph said. I thought I was going to disagree with some of it, but indeed, let me give you an example of how one of these sort of miracles happen. So if you think about the gap in the CFT, it's 1 over N1, N5 times 1 over Ry. And you think that's the incredibly low energy excitation that should be incredibly stringy in this system, because it's the maximally twisted sector and it's the lowest energy excitation. But what actually happens is that in these superstrata, you get these very, very deep throats whose base is macroscopic, many, 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 many times Ry. It's huge. But then what happens is this gap energy comes from the fact you take a big macroscopic wiggly wave whose wavelength is the size of the throat of the VTZ black hole, but it's the redshift that gives you everything. So in other words, that very low energy gap is created by big fat geometries where supergravity is a perfectly good approximation, but the energy scales are created by the redshift. And so I think this is something we still don't understand fully about holographic field theory is how we can access what seem to be incredibly low energy, very subtle, small excitations in macroscopic geometries. And we seem, there's some sense of, well, we can certainly do that. The question is, what is the limit to that? But we have examples where things that shouldn't have happened just work. And the best example I can think of just off the cuff is getting the gap energy right. That seems to be so stringy because it involves all these highly twisted sectors. And yet it's just a conspiracy of the size of the throat and the redshift.
Mm-hmm.
And so Joseph's absolutely right. When you chuck momentum on there, if you make a big fat 3-charge solution with a very deep throat, you can gain an awful lot of microstate structure by doing big macroscopic supergravity things at very, very high redshift. So it's, you know, so I suspect that there's going to be a lot more that you can do with that. The question is, how far can you go? The other side of the coin is, if you put one string in a microstate geometry, I don't think, you know, the back reaction of that will ever produce another microstate geometry. It's intrinsically a stringing excitation of a microstate geometry. But if I were an optimist, I'd say, okay, the phase space of all the microstates of a black hole have coherent expressions as islands in amongst this huge morass of states. And then around those, you can do all the stringing excitations around those, and maybe you can begin to connect up that moduli space. And maybe you can sample it with pretty high level of fidelity. And then Joseph's statement about, well, can I superpose geometries would be, can I transition between these islands? And so if am I optimistic? Not optimistic. I think this is real. I think we have very, very, very many of these coherent islands across the phase space. And then within those islands, you can do perturbation theory and string. And maybe that can give you the map or the charts that cover the whole space. That might be true.
Right, but still, would you say that these coherent islands are in a way like typical states, like, or atypical?
I think by their nature they're atypical, but that's sort of
just by looking at a 2-point function, right?
Yeah, but you should think of the islands as like cities on the Earth. I mean, you know, they're atypical states. They happen to have a lot of stuff in them, but the point is that you can, by small extrapolation around them, divine much of the planet. If you just take the cities of population 100,000, they're atypical. But if you explore 20 kilometers around each of them, you've covered probably a lot of the Earth, you know, land surface. And I think it's the same thing. There are atypical states that are highly coherent. Then you can look at typical excitations around those states in terms of stringing things. So you use the ground state as a background field, in background field method. You use the atypical islands that are coherent and then do stringing excitations in them. And at some point, those stringing excitations are going to require back reaction. And the minute you require to do the back reaction, it's going to move you in the moduli space of atypical islands. And so there will be a supergravity effect of that you should be able to see in supergravity, and then you can do perturbation theory around that.
Right.
That's what I'm hoping.
Okay. Right.
But the thing that's amazed me about the whole superstratum thing, and I think Joseph was sort of expressing the same thing, is, and Gary Horowitz once said this to me about 10 years ago when I was giving seminars on this, and we got the 3-charge states, we got these superstrata. He said, his comment was, "You've got far further with this than I ever thought you would." That's direct quote of Gary Horowitz. And that's the thing. We keep finding more of this stuff, and we keep finding ways forward where you shouldn't have expected them. And so it's one of these programs that just seems to give more the more you push it. And so, you know, I tend to be optimistic in this picture of, well, okay, if I can get these coherent islands sorted, then I can perhaps interpolate in between with strings. And if I put too many strings in, then it's going to back react and there should be a coherent island, and then I could perhaps thread the whole map. Right. But I think there's some cool things that even the people who don't like microstate geometries find useful. Is they take a microstate geometry and then they look at some stringy phenomenon in that background. So, you know, this tidal force calculation I did with Emil, I think a lot of people have appreciated it, because not so much because they like the microstate geometry program, but here's something you can do in something that looks like a black hole microstate that looks like an intrinsically stringy effect. So those kinds of calculations, I think there's probably quite a few of them that can be done. But yeah, no, a good dose of skepticism is always good, you know, because that Nietzsche, one of my favorite aphorisms from Nietzsche is that which doesn't kill you makes you stronger. I think that's exactly the microstate You know,
it clearly is miraculous how many things it has survived.
Yeah, and you know, I stopped giving talk about 7 or 8 years ago. I was giving talks about this, about 6 impossible things before breakfast, and because I had 6 impossible things that we had managed to get past in order to make these things. But that was 8 years ago, and I don't know how many impossible things we've gone past at this point, but it's more than 6. But so you know, it's one of these programs that just so I think the really important thing to do at this point, or at some point in the future, is to do the non-BPS story, the non-extreme or non-BPS. If we can get traction on that, that's you know, that's the really important thing, and finding ways through on that. You know, there's some really cool other questions I've been talking with Sean and so forth about how, you know. Here's another really nice example. I mean, the stuff I did on the tidal force with Emil is really cool, because originally we thought, okay, tidal force is going to disrupt stuff when it goes in and so forth. But what we found is that when we set a probe into a microstate geometry, you know, the calculation we did last year showed that it echoed back in a long time scale set by the N1, N5. So that was really cool. And we got this. But now we know there's no echo, because what happens is, because of the tidal force, the thing it excites the string and it traps it in the bottom. So stringy nature of matter in microstate geometries actually causes microstate geometries to trap stuff. So, you know, you're getting another black hole-like property out of a... I thought to do that, to trap stuff, we'd have to take energy out of the thing by dropping it in and then making it back react with the background. That's why I thought, okay, we've got to figure out how to do that. But no, all you have to do is drop in a particle, and secretly it's a string, and that string gets stretched and expanded, becomes massive, and gets stuck. So there's another gift from the microstate geometry program, is that it has tidal forces that create stringy excitations and trap things. 6 months ago, I'd have said, no, can't possibly do it. But no, it worked. So, you know, as a sort of research program, it just never ceases to surprise me what things come out of it, and what we keep finding. There are some, as I said, big unsolved problems. Most important is probably non-BPS. There are other important things along the lines of, you know, trying to understand what the multi-centered guys are. There's this huge phase space of stuff, which is the multi-centered guys. And on those, you can put superstrata modes. You can oscillate those, I believe. So this is a huge amount of stuff that we don't know how to construct. But what is it in terms of the holographic jewels? And you saw me in this talk today, in lecture, saying, I'm going to choose this, I'm going to choose this, I'm going to choose this. And every one of those choices were driven by the fact that my friends in London or in Italy tell me, oh, we know the holographic jewels of these guys, so this is what you should do. And so, you know, but the opposite is true. In principle, the geometry's got an awful lot of stuff in it, but we don't know what the holographic jewel is. So that's another big unsolved problem. Even in the BPS story. So there's non-BPS would be, you know, you give me a non-BPS microstate geometry with Hawking radiation, and I will be so happy. But you know, JMART doesn't count. JMART does count. It's a neat solution, but it's 10 years old, and it's so atypical. It produces such a weird set of Hawking radiation. Whereas, give me something which is much more typical, something which I know the holographic jewel. I can see it. I want to do something where I can do the holographic jewel in the CFT of this process and look at the Hawking radiation. You know, that would be really nice. Anyway, I'm getting tired. I don't know about how you guys are, but you're still with me 2 hours later, so that's pretty impressive. Any questions? So the next one will be next week sometime, possibly Tuesday, possibly Thursday, depending on when I get my act together. I've got to write it, but I'll put the notes up tonight.
Let me stop I'll stop